space-time fabric. So the 3 dimensions we can access. The 4th dimensions is unidirectional. We can't access it. In Interstellar movie, when that hero is going inside the black hole, he can access time also. That is why he was in 5th dimension. He can access space plus time also. He can go in future, he can come in past. That is why that 4th dimension was accessible over there. Okay.
So time is not a physical dimension then.
Over here, it's not. You can say it is also, it's not also. Now you have to see, you have to understand how do we go about it. First, let's see how gravity and space-time fabric are like same. Okay. Space-time can be brought off as a fabric in which objects of the universe are embedded. As you can see picture on the right-hand side, massive the object, it will bend, it will warp the space-time fabric. It's an interesting video. So now this cloth is like space-time fabric. Right now we are understanding it in 2 dimension. That is why cloth. Okay. That weight which is kept in the center, it's like planet or star or any heavier object. Okay. Let's see this video. So now that professor is actually throwing all the marbles. See, like the things which we saw in the video, they are moving around, wheeling around, and right now they are just coming closer to that particular weight and stopping, because they are not of the constant energy. When things have constant energy, like they are in the stable orbit, like our Earth is around the sun, it stays over there only. Okay. Okay, like an experiment which you can do in your classroom and understand like what is actually happening. This is the real representation of Earth in 3-dimensional space-time fabric. Now tell me, space-time fabric is pulling us down or pushing us down?
It's pushing us down.
Yeah, interesting, right? When you think of gravity force, it is pull. When you think of space-time fabric, it's pushes. Before we go ahead, let's go to the parts of the black hole. Let's see part of the black hole. So there are basically 2 parts of the black hole. One is called event horizon, okay, and one is called the singularity. Now over here, I was about to tell you about the Schwarzschild radius, okay. This is the equation. If I want to know the speed by which I can go to escape this black hole's gravity, I can use this equation. Similarly, the question which Prabhav asked, if I want to know the radius of the black hole, if it has sun's mass, I can use this equation and calculate. There are so many different terms, but this is the smallest equation to understand how things work. Okay. So event horizon is basically separating black hole from the outside universe. In basic terms, if I tell you, once you cross the event horizon, you can say there's no return journey. But to understand how that particular event horizon is separating black hole from the outside universe, we have one small analogous example. Everyone know about Niagara Falls, right? So consider you are in a boat. Right now, the water current is very slow. Nothing is happening. As soon as it reaches the border, the fall part, the water current is going very fast, right? Once you cross that water current, can you come back? Can you move your boat reverse?
No.
No, right? So you will go inside the fall, Niagara Fall or whatever you say. Same thing happens with the black hole. That event horizon, this is the event horizon. So basically there are 4 types of black holes. One of those are basically, you can say theoretical. They just appeared after a few lakh years after Big Bang. And they just vanished till now. Okay, they just got evaporated. Okay, so let's see those types of black holes. Those are called stellar black holes, intermediate black holes, supermassive, and miniature. Stellar black holes are the black holes which we normally know. For an example, a star which has mass 25 times more than sun's mass. When it's going to die, it's going to become a black hole. It's a stellar black hole. throughout the universe, you will mostly find stellar black holes because there are, same weight stars that appear. The second kind of black holes are, let's go with the intermediate black. Intermediate black holes are the black holes which are bigger than the stellar black hole and smaller than the supermassive black hole. We'll come to the supermassive. It's like medium black hole stars. We find very few intermediate black holes. Reason behind, for an example, one black hole is over here and one black hole is somewhere nearby. When those two black holes are come together, come together, and then when they collide, when they become one, they will become an intermediate black hole. But to see those kind of black hole, it's very difficult because the stars are at very far distance. As I told you, the nearest star after sun is at 4.2 light years. It's like very far. The third type of black holes are supermassive black holes. Those black holes, you find them at the center of most of the galaxies. The Milky Way galaxy has a supermassive black hole. And you know what is the weight of that supermassive black hole? Three different types of black holes. And you will be amazed to see the biggest black hole. So even Einstein was confused whether that can happen or not. But in reality, we got it. Black hole, if you would crush it beyond its Schwarzschild radius, this is our sun. If I crush it, to the size of a small city, it can become a black hole. Oh, sorry. Sun, yeah, Earth, like a peanut size. So this is one of the black hole. Its size is almost equal to size of a Manhattan, New York City. And its mass, it has 4 solar masses. Very small, right? One of the smallest. See, they are saying one of the smallest. Consider 4 times mass of the sun, but they are saying one of the smallest. Let's see. What do you mean by big according to them? This is the black hole in the center of the galaxy M82. It's called X1. Let's see this galaxy's, this black hole's mass. Its size is equals to Mars. And the weight is 1 ball equals to 1 sun, okay? How many suns? 1,000. And what do they call it? A mid-range black hole. Those squares are basically space-time fabric, okay? See how much they are like unzooming. That's a central black hole of a Phoenix cluster, star cluster. This is interesting. Can you see the size of our solar system? This is the black hole and our solar system is very tiny in front of it. That's a supermassive black hole. But the most interesting thing is the weight of this supermassive black hole. Now we are going to count the number of suns, okay? Ready? Thousand suns? No. Isn't it amazing? 20 billion suns. That particular supermassive black hole weighs equal to 20 billion suns. One of many supermassive black holes. let's see how much, like what is the size of our black hole. So it weighs 4 million solar masses, our galaxy center. It is also called as Sagittarius A star. This is the original image, okay? You see that star is moving like zoof. It's like different than the normal orbit a star must have, right? But you can see the central part. That's the black hole. This is one of the way by which you can calculate the weight of the black hole. So you know the weight of this star, you know by what speed it is moving around, you can calculate the weight of the black hole because it has the gravity, right? And we are just at the end of the presentation. Yes, this. Now this colorful disk is called accretion disk. When something goes very near to the black hole actually tears it apart. And you know, all the material which it has, it sucks inside it. Some of the material goes inside the black hole, and most of the material they move around the black hole because it's moving very fast. And when those things are moving, they actually rub to each other. For an example, helium, hydrogen, whatever it is, they are actually moving, rubbing to each other. Because of that friction force, they emit energy. And even black hole has magnetic field. Those energy radiation particles, because of the magnetic field, they like go up and down like jets from North Pole and South Pole, like Prabhav said. The energy waves, the radiation. The first picture of the black hole that we actually clicked few years ago, we saw the accretion disk. Third part is general relativity. Okay, the general relativity, the space-time fabric which we were discussing. As I told you, whatever moves in space, it moves on the space-time fabric. How? Like this. So if the sun is there, it is curving the space-time fabric. The light will always move from the straight line. Light will never bend unless and until it is moving on the space-time fabric. So the light is coming from here, it should go straight like this. But because the space-time fabric is curved over here, it goes like this. That's the end of the slide.